All right. Hello. This is my take for the proof method assignment for Professor Nasser's CST215 class. My name is Maverick Collins. And so we were tasked with building a couple different uh, algorithms, or utilizing a couple different algorithms in my case, to a output of prime numbers that um, are then computed to the perfect numbers, which are related to the Mersenne primes. And that's a given function to us that I'll show here. So this was given to me by Professor Nassar. This is kind of what our desired output was. This is how I designed my program. So first of all, he wanted us to take in a list of integers 1 to 20. And then we wanted the first task was to check to see if the list of numbers is prime. So that's what this column does, has all the primes 2, 3, 5, 7, 11, 13, 17, 19. You get the idea. The next task was to then take that prime number and then take it into this function. It's mirrored. I don't know if you could see that okay, but this was I think it's called the Mersenne primes, or the perfect number is what it's called, the perfect number. So it's these two it's this product between this I guess this is a prime number, and then this is a prime number. So that's all with the in being the input of these prime numbers. So I'm not a pure mathematician. However, I knew that we needed to utilize this, and I knew how to find the algorithms we needed to get this output. So basically, this is a simple, arithmetic that's going to be calculated. That's simply hard coded in this arithmetic in my code for to calculate each of these values, where n is the prime number. So after it checks to see if the list of numbers is prime, it's going to store it in a list, and then it's going to compute this product down the row. And finally, we want to store the divisors, what make this a prime number, in another list and output that with a format having a addition symbol in between all of the integers. So for 6, it's going to be it's divisible by 1, it's divisible by 2, it's divisible by 3. Okay. For 28, it's going to be 1, 5, 7, 14. You get the idea. And all the way down to 19, where the list gets pretty big. I think it's 37 numbers, if I remember correctly. So without further ado, let's take a look at my code. And I just realized that you're only seeing this paper on this little screen. So my apologies. I forgot that you see the exact same view that I see on my share screen. So hopefully you could read that, but you're about to see the output. So I guess before I describe the code, let's just run it. Okay, so there you go. That's kind of what I put on here, and I'll get into what we have. So you could see the 2, the 6, the 1, the 2, the 3, and the 3, the 28 from here. Yep. 4, 7, 14, 5, and then this is where it starts getting out of control. 5, 7, 11. I tried my best to put a delimiter here with these bars just so it's easier for you to kind of separate the numbers, and a tab down here in my print statement right here. So just try to clean it up a little bit, but it gets harder to, I mean, I try my best. These are all associated with 11, for example. These are with 13, as you could see, 17, and then finally 19. Can't even read that. That's 1, 2, 3. What is that? 137 billion something for 19. So pretty crazy, but let's look at what I put together. Um So the first thing we had to do is to check to see if a number's prime. And so that little script is right here. This is actually courtesy of Geek for Geeks. They had a pre-built solution that I, for the sake of time, utilized and implemented into my code. So I sourced that here and put my own little bits, as I commented here, dashed down here in the else statement. But by and large, this is their algo. So do not uh, intend to take any credit away from Geek for Geeks. It's a great resource. Similarly for this script, what we'll get to. So this checks to see if there's a list of prime numbers. So we're and this works for whatever input size you want. But for our class, you just want it up to 20. So it's going to store the lists, range 1 to 20, very simple, and then compute the list, and then it's going to store it back into the integer list. Where do we do that here? I guess we're not storing it. We're just simply checking it and outputting it. So it's not storing the primes as a list, even though we're creating one at the top. It's just outputting each number of the list down here. In this function where we're actually calculating the common denominators for a given number of the what's the math? This function here, right? So this was the Mersenne primes, or the perfect product is what I called it. And so what this is going to do is this number is going to be used to, where do I do it? Yeah, so this perfect product is going to be used down in this divisor generator. Uh, Again, this is courtesy of a person of Stack Overflow. I had a hard time trying to code this myself, so I figure if I get a working solution, I think there's a lot of work just getting all this stuff to prepare on one output, which there was it took me a couple hours just to get this to output what you see down below here in this pretty, well, not so pretty output. So without further ado, so yeah, so this is the given function that was given to us, that 2 to the n minus 1 multiplied by 2 to the n minus 1, as you can see here. So we're going to pipe that, I called it the perfect product, into the divisor generator, which is this function here. So this is going to then create a list where we are appending each divider, where it's going to check every number. So for 6, where 2 is the prime number, the perfect product is 6. 6 is then going to be piped down into this function, where it's then going to create a list. Sorry, this other screen I'm using just went out on me. Okay. Going to create a list of those perfect numbers and store them, which I'm going to, where did I put it? So yeah, here's the perfect product. I'm outputting that. And then my perfect list, which is right here. Yes, I'm storing the output of this function as a list. And then we had to cut off the first number in the array or list was 1. For some reason, the use case is working for 1. It shouldn't be. But he didn't want us to include, was it 1 or was it now I'm forgetting. Basically, I had to include this because I think it's maybe not 1. It's the very last number. Yeah, so it's 6. So it was including the very last number so like 6 is divisible by itself, of course, right? So it was appending 6 to the list. We didn't want that, right? We just wanted for 6, for 2 is the prime number. The perfect number is 6. For 6, we just wanted 1, 2, 3. We didn't want the last number in the set or list. So all this line, all this line simply does is cut off that last number. So anyway, so yeah, it runs down, collects all the denominators or divisors, I guess in this case is what we called it. And then those denominators are then going to be printed with a simple join statement with a plus. And then it did a little, like reiterate at the very beginning of this, formatting just so it's easier to read for the user. And this is what you see now. So I got as close as I could to what he showed me in his office hours of kind of what he was looking for. I think it's pretty dang close. I hope I'm not missing any other parameters. So it was a challenging assignment. A lot of different elements were utilized with the prime factorization, with the perfect numbers, with getting it all output, not having a example output to go off of, which we've had, and definitely could see the progressing. So challenging assignment. I enjoyed kind of getting it all to work. These two functions getting to work nicely together in this little else statement, and a little nervous for the subsequent assignments, but I'm sure we'll get through them. So thank you for your time. Thank you for grading, and we'll see you in the next one.